So we're gonna finish up talk about encryption. I might finish up all of the encryption content today. Then the last 5 lectures of the semester, what I want to do is build and deploy an app and show you the entire process of building a web application. And I will use libraries for that. I'll show you the whole process of effectively making your project, but with a different feature set. And then deploying and getting SSL certs like we're talking about today. So I want to go through that whole process. So let me clean up the rest of the slides that I have that I want to cover this semester. And then we'll get into more open-ended building a project and just live building a project. All right, so let's get into encryption and finish this one up. Oops, we covered all that. I need to go down here. We just have the last few slides of this slide deck. So we talked about encryption, just a very brief overview. We talked about RSA and how it uses math to generate a public-private key pair. And then those are used to encrypt. We either take the public key and encrypt in a way that that message can only be decrypted with the private key, so we know only the intended recipient can read that, or you can use the private key to encrypt, which we call signing a digital signature, and then broadcast that out. Everybody can read that message, and they can verify that you are the author because you should be the only one with that private key. So we can both encrypt and sign our digital traffic using public key encryption. But this isn't quite enough. There's a very powerful attack called the man-in-the-middle attack, which completely destroys our thought of security when it comes to public key encryption. So there's one huge flaw with this public key encryption system that needs to be solved. And don't worry, we got a fix for this called certificates, which you've probably heard of, I would assume. If not, you're going to learn a whole bunch today. You're going to learn a lot of good stuff. So with this attack, so one big flaw with this is I have to send if I'm a server and I want people to send encrypted messages to me and I want to send encrypted messages to them, the very first thing we have to do is exchange our public keys. So if I want somebody to send encrypted traffic to me, I have to send my public key over an untrusted internet through the Wi-Fi and send that to this user who wants to connect to me. The user has to do the same thing. They send their public key over to me. If they want to encrypt using public key encryption, they have to send their public key to me so I can encrypt things to send to them. That has to happen to get public key encryption to work. These public keys have to be communicated. They have to be transferred over whatever means we have to communicate, which is the internet. That communication inherently cannot be encrypted. We can't encrypt the public key because we haven't set up encryption yet. So the man-in-the-middle attack says, okay, well, if I can intercept that traffic, I'm going to grab that packet out of the internet. If they can control a router, for example, they hack into one of UB's access points, and they get in there and they start intercepting traffic. They're going to say, well, when you're sending this public key out, what I'm going to do is intercept that traffic, not send that to the user, replace the public key with my public key, and then send my public key to the user, but leave everything else intact so it looks like it's coming from the site that they're connecting to. So now they get a public key. It looks legit. It looks like it's from the site that they're trying to connect to. They say, oh, cool. They get that public key. They encrypt with that public key, thinking, well, only the site that I'm connecting to can read this information. They send that message. Of course, it was encrypted with the attacker's public key. The attacker intercepts that message. They decrypt it. They read it. They formulate a response. They encrypt their response and send it back. And you're just communicating at that point with the man in the middle, the attacker who launched this attack, and you're never actually communicating with the website that you expect to be communicating with. And then they just read all of your traffic. That you're interacting with them as though it's the actual site. This is a very bad attack, something we don't want. And even if the man in the middle isn't that malicious, they can still forward your packets to the legit site, and they of course know the correct public key for that site, so they can decrypt what you encrypted, change the message, re-encrypt with the proper public key, and then send that to the server still, and have you still communicate with the server, but they're modifying and reading everything that you're sending. So this is a very bad attack. It completely wipes out any idea of security or encryption, privacy. It's all gone. You're just communicating with the man in the middle. And honestly, if they're launching this attack, if it's a site where you have to authenticate and log in, which presumably it is, because why would you attack a site where everything's public anyway? The attacker can just go there and read everything, unless they want to, change what you're posting or whatever. I don't know. But the first thing you're going to send that site, it's going to be your username and password, right? Even if you're logged in, even if you have the right cookies, guess what? The attacker doesn't care about anything about you. They're just going to send you the login page. They're going to say, here's the login page. Send me your username and password. You're going to be like, okay, I know passwords are plain text over the internet, but don't worry, it's encrypted, so I'm good. You encrypt it, you send it, but you encrypted with the attacker's public key. Attacker decrypts it, reads your username and password, and then they can just leave the man-in-the-middle attack. Maybe your session expires and you get some weird error in your browser. Then you just reconnect to the legit site. Meanwhile, the attacker has your username and password, and it's open season on all of your data and all of your everything. If it's a banking website, think of that. You're done. Like, they have all of your stuff. So this is the attack. This is what we have to prevent. And we're going to have certificates prevent this attack and certificate authorities. So a certificate authority, how could you tell if this is happening to you? You kind of can't. What we do these days is use certificate authorities and certificates, and then we just assume it's not happening because with a certificate authority properly set up, they just can't do that. The attacker, we completely eliminate that attack unless somebody gets a root CA key and a root CA cert installed in your machine. That's the one way that they can do it. But when that happens, there are so few of these. When that happens, it makes news. Like you'll know about it. And patches come out right away. Use the latest up-to-date browsers, and you'll know about it. There was a pretty big root CA attack a long time ago. I say a long time, but a long time in internet time. So like probably 5 years. I don't know what the timeline was. But let's talk about what CAs are, and then we just assume that it's not happening because CAs are a pretty solid idea. So a CA is an entity with a trusted public key. And this is one of the fundamental flaws of all encryption and all security, by the way. It always, everything has to start with some assumption of security. So we have to have something that we assume is secure, some communication that we assume is secure. If we can't start somewhere, we can have to assume that everything's corrupt or everything's compromised, rather, and we have no security. So we have to start with some assumption. Our assumption for encryption on the internet is that we have these root CAs installed through our operating system and through our browsers that have a known list of public keys that we're going to trust. And we're going to assume that that installation process went smooth. Like nothing went wrong there. So this isn't necessarily internet communication. You downloaded this from the internet. You can verify the file. You can get a hash of the file and verify the file. If you want extra security there. If you ever seen where you download something, it says like, here's the SHA and MD5 hash of this file. What you do is download the file and then you hash the entire file. Make sure the hash matches what they provided for you. And then you can have a pretty strong assumption that that file was not interfered with during the download process. So if you ever wonder what those are, that's what they're doing. So you can check the hash of the file, make sure nothing was modified during the download process. And we usually assume that your operating system, while you're installing the operating system, that nothing went wrong there as well. So when we get these root CA certificates, that's where our assumption starts with, that our root CA certificates, or rather public keys, I haven't talked about what a certificate is yet, but the public keys for the root CAs, what we call a root certificate authority, We assume those are secure. We assume those are correct, that those have not been subject to a man-in-the-middle attack, that those are the actual valid certificates for those root certificate authorities. It's where everything starts. All encryption on the internet starts with that assumption. If that's false, which every once in a while it is and it makes news, that's bad. But we're going to assume that those are all solid. And then once we have a site that we want to connect to, that site's going to send us not just their public key, but their public key signed by one of these certificate authorities. So when we have a public key, we're going to generate our public and private key, or have the root CA, or have the CA generate those. We're going to say, hey, can you sign these for me? They're going to sign our public key. So the certificate authority, or the root certificate authority, is going to sign our public key. And then we get a signature of that public key, along with some other security information, what algorithms we're using and things like that. And that's what we call a certificate. So the certificate authority is going to take our public key, verify that it is us, verify that we control that domain, and then sign our public key and send us the signed public key. That's our certificate. That certificate is signed by their private key, by the certificate authority's private key, and everybody has the public key installed on their operating system. Everybody has their public key already installed. So when you send a certificate, when that server sends a certificate to a user, the user takes their certificate authority's public key, verifies the signature, and verifies that that public key, your public key, was not tampered with, and that that is in fact your public key, because the certificate authority signed that public key, and you have the certificate authority's public key, so you can verify that signature. That makes it gets a bit wordy in there. Does that all that make sense? Is everyone good with that? It's a lot of public key goodness going around. And these things are there's layers of security with these certificates. This is a signed, and the signature has, or the certificate has do we call them fingerprints? I think we call them fingerprints. A hash of the certificate to make sure that the certificate itself wasn't tampered with at all. So if anybody wants to tamper with a certificate and forge one of these certificates, what they have to do is break cryptography and hashing simultaneously, because we have a cryptographically signed certificate and also a hash of that certificate. So if you change the certificate, if you decrypt, change it, and then re-encrypt it, the hash isn't going to match because you just changed the data. So there's several layers of security here. A lot of things that an attacker would have to break in order to forge one of these certificates. One more time. So we have public key encryption. You generate a public-private key pair. You give your public key to everybody, and then if somebody wants to communicate to you, they encrypt with their public key and then send the information to you. You decrypt with your private key. The question is, how do we ensure when we're sending out that public key that it wasn't tampered with? So what if an attacker takes your public key when you're saying, hey, here's my public key, let me send it over the internet. An attacker intercepts that, replaces it with their own public key, and then sends their public key to a user. Now they have the attacker's public key. They encrypt in a way that only the attacker can read those messages, and I can't read those messages anymore if I'm that server. So what we do is have a certificate authority generate their own public-private key pair. The certificate authority sends everybody their public keys in a assumed secure way. It happens when we install our operating systems and when we install our browsers. I actually have to look into that. I don't know if browsers actually add more certificates, more root CAs. to your list, or if it's just the operating system. But in installation processes that are assumed to be secure, we get the public keys of the certificate authorities. Now, when I'm a website, I'm a web server, and I say, okay, I want to make sure that I send this public key to my users in a way that's secure. What I do is talk to the certificate authority first. I talk to the certificate authority and I say, I want to start, sending traffic over HTTPS. I want to be secure over the internet. What their certificate authority does is signs my public key, cryptographically signs my public key with their private key, and then says this public key belongs to CSE312.com. Now I have what's called a certificate. It's a cryptographically signed, my public key, but cryptographically signed by the certificate authority. Now, when somebody wants to connect to my site, I don't send them my public key, my raw public key directly. I send them my certificate. They get their certificate. They have the CA's public key, so they verify the signature, and then verify that this certificate was in fact signed, cryptographically signed by the CA, so they can verify that the CA did verify this information, and that information says, here's the public key for CSE312.com. And that certificate also contains a hash of the certificate, which I believe we call a fingerprint, to verify even further that that was not tampered with. And that's how internet security works. That's how internet cryptography starts, at least. That's where it starts. So if you look at a certificate, most certificates, in fact, I've never seen one. Maybe, I don't know. But most certificates are not signed by root CAs, by the CAs that are actually installed on your machine. Most of them are signed by some other certificate authority that's not a root CA, where we don't have the public key stored on our machines. So how do we know that's secure? Well, the root CA signs the cert of a non-root CA, and then the non-root CA signs the cert for that website. So we have what's called a key chain, where we have a CA, and there might be multiple layers here. A root CA signs a cert for a CA, which signs a cert for another CA, which signs a cert for another CA, which signs a cert for the website. As long as the cert chain, the key chain from that website originally started with a verified root CA, then we call that a valid chain. We know that there's some chain of security there that leads to a root CA, so we're good with that. If the key chain does not end in a root CA, it's what we call a self-signed certificate, and it should not be trusted because it's vulnerable to a man-in-the-middle attack. So if we go to a site, and we'll go to 312.com because I have it right here, we can check out the certificate. And this certificate was signed using SHA-256. The public key is a 2K RSA key. There's my public key for CC312. This was signed by, if we can see it, and then it verifies, this certificate is specifically for CC312.com. I can't take this cert and move it to CC116.com. It's a completely different cert with a different public key. Because they signed this cert specifically for CC312.com. And when I get this cert, I have to verify that I am the owner of CC312.com. And I missed... Oh, here it is. No, I don't want it there. Issued by R3. Issuer. R3 Let's Encrypt USA. So I use Let's Encrypt because they give certs for free, and they have very nice tools. A tool called CertBot, where you just type a couple of commands in the command line, and you just get your cert. It's super handy. It's nice, concise. I don't have to remember all the small details about certs every time I want to install a cert. Just run their commands, run their scripts, and it's done. So R3 Let's Encrypt is not a root CA. And if we go into... I always forget how to do this. You saw me do this with plugins earlier. This one's not as bad. I know how to find this one. Can I get there from extensions? Now I'm only going to be able to get to extensions. Oh my goodness. Okay. I got this. Manage certificates. All right. So if I look at, I can look at my certificates. You can do the same thing. You can see all the certificates that you have installed on your machine. And I don't know why I can't resize these boxes. And I can go to Trusted Root Certificate Authorities, and I can look through this list and find all of the CAs that are Trusted Root Certificate Authorities. And you can see some common names, some big names in security, and just big names in general. Microsoft, Google's in here somewhere. GoDaddy, apparently. Where are the Google ones? Well, anyway, there should be some Google ones in here too. VeriSign is a big one. And nowhere in here are you going to see that R3 Let's Encrypt. I can't get out of that. You're not going to see that anywhere. This R3 Let's Encrypt US. That's nowhere in there because I have this path where that R3 certificate, which is itself just a certificate that was signed by another certificate authority, this DST root CA X3, and that's actually the root certificate. It's not signed by anyone, issued by itself. It is technically a self-signed certificate if you want to look at it that way. And this should have a very large key size. Well, I guess they're doing 2K for all these certs right now. And this is pre-installed on my machine. If I go back to settings and I check out my Trusted Root certificates. Oh my goodness, I forgot what it was already. There it is. DST root CA3. That's the root CA that chain leads to. So since you didn't get any security warnings, assuming you didn't get any security warnings when you go to cc312.com, that means that the cert is valid and that you have this exact certificate installed on your machine. And you could look at the public key and it'll be these exact bytes on your machine. We both have this exact certificate installed on our machines. And probably this entire list. You have all these certs. So when you go to cc312.com, you get the security, everything's good, everything looks good. If the cert is installed and it doesn't lead to a root CA, that's where you get warnings. This site is not secure. Your information is not private. It's not protected. That's when you don't have a cert leading to a root CA. Let's get through all these. And that's what HTTPS is. We encrypt everything. Slap that S on there, it means we're encrypted. Our communication is going over TLS. We call it HTTP over TLS. Or previously SSL. Once SSL, got cool enough, it had to change its name. For some reason, once they hit past version 3.0, they said, you know what, let's start calling this TLS instead of SSL. It's the same thing though. Transport layer security instead of secure socket layer. I don't know why they changed it, just to confuse us. SSL and TLS are the same thing. TLS is just the newest, latest version, effectively SSL 4.0. So HTTP over TLS, and that adds to the network stack. So before we have our HTTP, which communicates over TCP. You have your TCP sockets in your code, and then TCP is communicated over IP, and then you focus on the HTTP layer. We're doing the same thing now with HTTPS, except we have HTTP as its same layer still, but instead of directly connecting to a TCP socket, you go through a TLS layer, encrypts everything, and then sends it over the TCP socket. So HTTP and HTTPS are exactly the same protocol, except there's this TLS layer in between your HTTP and your TCP. So if I had the homework, which I used to have last year, where you have to add HTTPS to your sites with a self-signed cert, what you do is go into your TCP library and say, go into the documentation, go, okay, how do I install a TLS cert into a TCP socket? And then there's some documentation. You say like socket.add cert and use HTTP or use TLS. You install the cert on top of your TCP socket, and then the libraries do the rest for you. Your app doesn't change at all. Just when you're sending that information, there's a layer that's encrypting before sending your responses over the TCP socket. That's the only difference. And decrypting when messages are received. You as an app developer don't have to change anything you do. You just add that TLS layer in there. Bam, HTTPS. Do not change your apps at all. None of your code changes, which is super fantastic. It's a very nice convenience to have, where we just encrypt all the traffic and don't think about it from the app development side of things. Why does this slide exist? Oh, to make the point that I just made. That's such an important point. I wanted to make sure I said it early. You don't change anything you do. You just slap TLS on top of it. So TLS is going to encrypt all the traffic to and from the server. But everything we've talked about only helps us encrypt traffic to the server. There's one pretty big problem. So one way we could solve this using what we've talked about so far, say when the server sends something to the user and sends sensitive data to the user, we would like to encrypt that too. What we've talked about so far, to use the technology we've only mentioned so far, the user would have to generate a public-private key pair, get their public key signed by a certificate authority through a keychain that leads to a root CA, and then send the certificate to every website they want to communicate with. And then the website would have to encrypt using their public key and then send the traffic to the user. Painful at best, prohibitive at worst. We're just not going to do that. It's just not how we're going to do things, and that's not how the internet works. So we're just not going to do that. So what do we do? And there's another problem. There's a few reasons why we don't do that. We actually don't use, ready to just shatter the last couple of lectures, we actually don't use public key encryption to communicate over the internet. Boom. Just all that we talked about. We actually don't encrypt using public key encryption. One big reason for that is it's freaking slow. It's very slow. If you had to encrypt and decrypt everything on both ends of the communication, loading times would increase. CPU usage would ramp up. Maybe not to significant amounts, but enough that it's going to hurt performance. And web servers would really see the energy costs go up. So we actually don't do that. And we had the problem of the client's not going to generate public-private key pair and get their public key signed by a CA. So how does TLS actually work? Using symmetric key encryption. With symmetric key encryption, we're going to communicate using a shared common key. So the server and the client are both going to have the same key. The same key both encrypts and decrypts. So when either one of us want to send information to the other, we're going to encrypt with that symmetric key, send the information, and then the other side is going to decrypt with that same key. Symmetric key encryption. So what we need is an encryption key that we both agree upon, that only we know, the client and server know, for a specific connection, and that was communicated securely. So this sounds like we just took a lot of steps backwards. We went all the way back and said, okay, how do we do encryption again? And we're going to use this different encryption key. So this is what TLS does. The TLS handshake, everything's got a handshake in these connection protocols. The TLS handshake negotiates this symmetric key. Generates a symmetric key that is going to be a session key, meaning it only lasts for that one session, that one round of communication with the server. And do so in a secure way. So we want to communicate effectively and securely to agree upon this symmetric key without opening ourselves up to an eavesdropper or a man-in-the-middle attack or being vulnerable to just packet sniffers or whatever we have going on. Whatever attackers are out there, we want to agree on a symmetric key without anybody being able to break our security. So here's the setup that we have. That's what we need to solve. We do have ways of generating these symmetric keys. A symmetric key, luckily, we really what we need to do is just agree on some sequence of bytes that's long enough that it's going to be secure, that's going to have enough entropy. So we effectively just have to agree on a number. And we have to agree on the same number. And then we can use that number to generate keys and use different symmetric key crypto systems. But we have to agree on a number first. One way to agree on such a number is using a Diffie-Hellman key exchange. We're going to agree on some value p, which is a prime number that's a generator for a field, meaning that we get a lot of entropy, a lot of different values can be generated with this number. If we keep raising this to different exponents, we're going to cover every value in mod p. Raise it to an exponent mod p. The generator g. A g, which is a generator over the prime group p. This is where I have to remember all my abstract algebra. Where g raised to the first power is going to be g, the 0th power is going to be 1, and then squaring it mod p is going to give you another new unique value. And if I keep multiplying g by itself or keep raising it to different exponents all the way up to p, I'm going to get unique values for every single exponent that I choose. So g is called a generator because g raised to an exponent mod p is going to cover every single value from 1 to p minus 1, or 0 to p minus 1, I should say. Or do we exclude 0 because that would mess up the values? But we're going to, because 0 would just 0 everything out. So 1 to p minus 1, it generates every single value there with different exponents. So we get maximum entropy out of this. We get the entire thing. So we can have values that are not generators, which get like for example, 2 wouldn't be a generator because we're going to get 2, 4, 8. Would that necessarily be true? I'd have to think about that one. But we might get something that gives us only half of these values. So we want to make sure the value we get gives us equal representation over this field. And these are part of our public communication. Everybody can know what P and G are. And then the private communication, both the server and client generate random numbers that are not shared with anybody and not even shared with each other. Nobody sees these values. Client is the only person on the planet who knows A. Server is the only person on the planet who knows B. Both client and server are going to take G mod their value, or raise to their value mod P, and send that to the other side. The other side is going to raise whatever value they receive to their value. So the server computes G to the B mod P, sends that to the client. Client computes, takes this value, raised to the A mod P, and server does the same thing mirrored on the other side. So after this, both client and server have the value G to the AB mod P. And that's their private key. That's their symmetric encryption key, is G to the AB mod P. They both have the same value, and nobody else can compute this value because anybody eavesdropping on this, they either have G to the A mod P or G to the B mod P. And that's it. And they can't generate the other one. To be able to generate it, they'd have to solve the discrete log problem. And we're going to make sure these values are large enough that that's infeasible. So even with both of these values, an attacker can't compute G to the AB mod P. So this is one way that we can exchange keys in a mathematically secure way. And that's how we generate a symmetric key. This is used as a symmetric key. It might be thrown into an algorithm to generate a symmetric key. This might be the seed to an RNG algorithm. And then use something like AES to be able to encrypt. This is a symmetric key encryption system. And then we use that to generate a key to be able to communicate back and forth. And AES has the advantage that it's very fast encryption. So to be able to communicate this, we have the TLS handshake. The client says hi. Server says hi. Through these hellos, they agree on which algorithms they can communicate. So the TLS protocol itself doesn't define any protocols. It doesn't say we use RSA, we use AES, we use SHA-256, we use elliptic curve encryption. TLS itself doesn't specify any of that, but through the initial part of the handshake, the client and server are going to agree on what algorithms they support, and the server is going to decide. It's going to look at the client's list of algorithms they support and choose one of those, or if the client is super outdated, it might just say, I'm not supporting any of those because those are all insecure. Those are provably insecure. Server's going to send its certificate. Client and server are going to generate their A and B, or assuming they're using Diffie-Hellman, their exchange here might say, we don't use Diffie-Hellman, we use this other cool new technology. But they're going to generate their parts of the symmetric key and send them to each other. And the server is going to sign their G to the A. Didn't I say G to the B? G to the B. The server is going to sign their G to the B when they send that to the client. The client is going to encrypt G to the A when they send it to the server. The client has the server's public encryption key. So the client can encrypt this with the verification that they have the proper public key and that only the server can read that. They're going to encrypt this, send that to the server. The server is going to sign G to the A mod B with their private key, which can then be verified by the client. They both have their partial keys. They generate the symmetric key, and then they start encrypting using that symmetric key to communicate back and forth. And then the actual encryption over the internet is using those symmetric keys. So notice that, I already mentioned this on the previous slide, but maybe I don't have it explicitly on a slide, but notice that all of that stuff we did with certificate authorities, signing certificates, getting our domain names verified and our public keys signed, all of that was just to communicate our halves, our partial symmetric keys using encryption. Without that, TLS doesn't work. The symmetric key, this key exchange generating a symmetric key doesn't work if we can't secure our partial symmetric keys. So all of that setup with certificate authorities and root CAs being installed by our operating system, signing certs, all of it is just to be able to securely exchange our partial symmetric keys. We used that twice. We encrypted this and we signed G to the B mod P in this example. That's it. And then the actual communication over the internet is encrypted using symmetric key encryption. So we didn't use public key encryption very much. We don't use it very much. But when we do use it, it's very crucial. It's very important. Or else, of course, these would just be susceptible. Both of these communications would be susceptible to a multitude of attacks. G and P are public. All an attacker has to do is come up with some value C and swap out B for C. And there's no security at all. Zero. So this is the only communication that we secure using public key encryption. The client never even generated a public-private key pair. They don't generate public-private key pairs at all, at least in this scenario. Again, the algorithm is... The TLS is flexible enough that it could allow that. But for that example, and for most cases, the client's not going to generate a public-private key pair. We also get something, using setup like this, we actually get something called forward secrecy as well. This is a very important idea, a very important concept, where, say, an attacker intercepts all of your encrypted communication with a client or with a server. Maybe it's sitting really close to the server on the internet, has a, one of the routers right outside of that server, and is just intercepting every piece of information from that server and to that server. It's all encrypted, but they just store all of that information. And then at some point later in time, they're able to attack that server's cert, and they're able to recover that server's private encryption key from their cert. And then they decrypt everything, and now they read this entire multitude of potentially years of communication. Just go back in time and just read everything that's ever happened. Everybody that's ever communicated with that server, they just read it all, including passwords, of course, because passwords are only encrypted, are only protected by encryption. So they get everybody's passwords that is logged in over that time, all kinds of information. What forward security says is even that attack, you're not vulnerable to. And we do get this the way we're using TLS. So since all the traffic was encrypted using a one-time symmetric key that's unique to that session of that user, even with that type of attack where they're storing everything and then breaking the encryption key later, the attacker still can't read those messages. This is what we call forward secrecy, and that if somebody breaks the encryption key later, they still can't read the old messages, because they still can't generate that symmetric key without breaking discrete log in our example. They still can't break that. Then later communication, they can do man-in-the-middle attack and replace A and B with their C and D, and then generate their own symmetric encryption key and have all kinds of live attacks like that. But they can't have offline attacks with this property. And to end on kind of a little bit of a downer, I guess, now that I think about it that way, is we have HTTPS, everything's encrypted, everything's fine. But guess what? And let me go all the way back to the beginning. So TLS was right here. So everything in our HTTP, everything from our servers, like our apps perspective, is encrypted. But guess what's not encrypted here? TCP and IP. These can't be encrypted. I guess TCP could be, but IP certainly cannot be encrypted, because IP is used by the routers of the internet to figure out where to put your data. So no matter what kind of encryption, no matter what kind of technologies, well, I shouldn't say that, but what kind of encryption you use, your IP address is still in the clear. And the IP address of the server you're communicating with is still in the clear. So anybody can read the IP addresses, the destination and source IP addresses of every packet on the internet, because we can't encrypt that. How are we going to encrypt that and then still expect the routers of the internet to route our packages? It'd be like sending a letter in the postal system and scribbling out the addresses, the to and return addresses, and then expecting the mail carrier to still deliver that to where you expect it to be. No, that information has to be public, because that's how we get things to where they're supposed to go. So these still have to be in the clear. This is something that we can't hide. Even no matter how incredible our encryption gets, we can't hide, at the very least, the IP. The TCP, theoretically we could, but the IP, we cannot. We can't hide that. So this is why, even with encryption and all this cool math and everything, this is why VPNs are still very popular. This is why you see VPNs advertising all the time. Because they do offer a way to at least partially hide your internet traffic a little bit. Because even though with HTTPS, with encryption, people can't see what you're saying, they can still see with whom you're communicating, what servers you're connected to, what sites you're visiting. And then from that, they can start inferring some things. Okay, you have gigabytes of traffic going to this torrent server, well, that's a bad example because that's all peer-to-peer. But you're communicating with this really shady site over here. Well, you can kind of piece together what you're doing. You're visiting these 3 sites and they tend to work together. There's things they can figure out. So the VPN helps that by bouncing your traffic off of a VPN server. So people can still see that either they're on your side of the communication, they can see that you're connecting to a VPN, but they don't know what you're doing after that. They can still see the IP address of the VPN, though, and see, oh, you're connecting to a well-known VPN IP address. Or they can see the other side of the traffic and see that you're connecting from, there is traffic from a VPN, but they don't know that it's you. They don't know who's on the other side of that. So you can hide at least half of your communication and get closer to privacy using a VPN and encryption with root CAs and all that good stuff that we talked about. So the VPN server depends on the fact that the VPN has enough traffic to conceal which traffic is yours. To an extent, yes. Like if it's a well-known VPN, yeah, and there's enough traffic. But even if the VPN had just one user, you were the only user, someone would have to be able to see both sides of that communication. So if they were sitting like right outside of the VPN and they could see information coming in from your IP address and then something coming out of the VPN going to a specific server, then they could infer that that's you. But they have to be positioned close enough to the VPN to see both the incoming and outgoing packets. So if they're not, if they're only positioned, like maybe it's the app itself, the server itself, trying to determine who you are. Maybe you're making a Google search and you don't want Google to know that it's you making the search. They're not going to be able to figure out that's you. Well, given that it's Google, they probably have some way. Because they won't see the traffic coming into the VPN to know your IP address from that side of the communication. So they still might not be able to find out, even if you're the only user of that VPN. But if they have the resources and they have routers and traffic monitors, I guess, sitting at the right parts of the internet, they would be able to figure that out. Like a tier 1 network would be able to figure that out, for example. Yeah, bouncing off multiple servers it's harder to track. At best, it'll take them, or at worst, it'll just take them longer to figure it out. Like, that's how onion routing works. And the Tor network is an onion router. You just go from effectively VPN to VPN to VPN to VPN with different encryption along the way. More encryption, more layers of encryption at each step. Wireshark next to the VPN server probably wouldn't work. I would imagine that the VPNs aren't using wireless. VPN, anybody selling VPN service should be aware of all the security issues, and not have that. What somebody could do potentially, I don't know how this is where my knowledge hits a wall, and I don't know how the attackers physically pull these attacks off, But to speculate what you could do, which is sounds like something from the movies, and that's probably why I think of it, because I've probably seen it in a movie. But you actually go to the wires. Like there are physical wires that take our traffic. If you clamp onto that and read the bits moving through that wire, then you can get that information. So you find the building for the VPN, you find the big data center, you find the big wires going into it, which might be underground. Maybe you got to dig to find them, clamp onto them, maybe cut them, splice your hardware in the middle, and then hook up all the wires. I mean, somebody would really have to want to get your data, is what I'm saying there. What's more feasible is that VPN has to pay for internet access. They're paying somebody for internet access. Like somebody owns the hardware that they're plugging into. Either a tier 1, probably a tier 1 network at that point, or an ISP. The people who actually own the servers that are routing traffic through the internet, they can very easily see everything that's going on. So if you're at the level, if you're thinking, I don't trust these major corporations, I don't think they have my best interest in mind. Corporations that you don't even pay money to, by the way. So they don't even have an incentive to have your best interest in mind. That's more of where it's a lot more feasible. Or even just one rogue employee at a company like that, at an ISP or a tier 1 network. That's more of what we're concerned about. Or if you're paranoid and you don't want the government knowing things, like the government has resources. They can find things out. They can subpoena those companies and they can get that information. So if you're doing something less than savory, you might be concerned with that. All right, and I'm starting to get into opinions too, so let me cut off the YouTube. See you, YouTube.